So let's continue with Boolean algebra, and we are in logic minimization. We talked about the ad hoc method, Boolean algebra, and now we are talking about some examples. The first example I'm going to do is the famous overflow circuit. Okay. I want to do much the same as what I did with the ad hoc methods, except that now I like to use the rules of Boolean algebra to manipulate the circuit. Okay, so the very first circuit I do is this, and what I want to do with this circuit is the following. This circuit is using ands and ors, but then I don't like ands and ors because they cannot be realized directly in CMOS, and therefore I want to use nands and nors maybe. All right, so what I do is I write the equation. The equation is the Boolean equation for the overflow is let me do this by hand. That would be a lot more understandable. So I have V is A bar, B bar, ended with C instead of S, A, B, ended with C bar. Okay, and what I do is I use the very first rule. The very first rule says bar it twice. Okay, bar it twice. The very first rule, it says if you bar something twice, if you complement something twice, is as if you haven't done a thing. Okay, so I do this. The last rule says you can take the bar and break it from its upper level operation. See here, I have A bar, B bar, C, ORed with A, B, C bar. These are the bars. Bar, bar. Okay. So this is the ending. Then again, I have this bar here. Then this is the ending. And then the top level operation is OR. Okay. Break the bar on at its top level operation. What it means is break the bar right here, because the top level operation is this OR here. What this becomes is a bar here, A bar, B bar, C. That's De Morgan's. OR changes to AND, A, B, C bar. Okay? Now let's do this. What does this expression say? This expression says this is what? A bar, B bar, C NANDed together, and therefore this is a NAND. This expression says, again, A, B, C NANDed together. This is the second NAND. Then what does the rest of this expression say? The rest of this expression says this. It says that the two red circles are NANDed together like that. Because they're ANDed, and then there is a bar, that means a NAND, and therefore you change this to an AND. What did I do? I used the first rule and the second rule without having to do ad hoc methods and turn my circuit into a NAND circuit. Okay? A simple example using only two of the rules of Boolean algebra. when we have something like this is 28 transistors. If we turn it into transistors, and then by simple manipulation of Boolean algebra, I use that circuit, turned it into this circuit. By the way, the output NAND, which you see over here, is no different than this. Why is this? Well, here. A bar ORed with B bar. Okay, is A and it with B bar. What rule says that? Well, actually, De Morgan says that. De Morgan also says A or B bar, that means the NOR of AB, is A bar ended with B bar. That's De Morgan. That's why we take this and say this is an AND, but when we like it, we say, well, this is also an AND. And therefore, the circuit that you see over here is no different than this circuit over here. The output is, again, another NAND. In any case, I used Boolean algebra using De Morgan. I have this circuit. This circuit only uses 22 transistors. What it means is by Boolean algebra manipulation, okay, I'm able to turn a circuit into fewer transistors, fewer gates, a faster logic, and so on. Let's take this circuit, and I'm trying to build this circuit, okay? First of all, this is A and B. Needs a correction here. A and B. Sorry, A and C, which is this third one here. B and C, B and C. This is the this is B and C. This is A and C. This is A bar and B, all ORed together. Okay, that's a circuit. If I want to build this circuit, I have 4 transistors here, 4 transistors here, 4 transistors here, 2 here, and 6 here. That's if I turn it into all NANDs and all that. Okay. I take this equation, I say, well, there's probably something I can do with this equation. So this is what you do. You say, well, let's take AC, keep it as is. Let's take A bar B, keep it as is. But then let's take BC and it with A or A bar. Now, A or A bar is 1, right? A or A bar is 1, and therefore ANDing BC with the 1 doesn't matter. That's the same thing as BC. Why do I do that? Well, because I like to do this. Okay? Then I keep AC as is. I don't touch it. I keep A bar B as is. I don't touch it. Okay? And I take BC and A. I apply distributive law, and therefore this becomes this, and then A bar BC becomes this. I just applied distributive law. Why am I doing this? Well, to be honest with you, because I've done this before. Okay? Next, I take this equation that you just saw here, and I call AC, I call it AC ANDed with 1. Do you mind? No, because A ANDed with 1 is no different than A. Okay? So I just add a 1 to AC, so no problem. I keep ABC. I can arrange the order of the variables any way I want, and therefore ABC is no different than ACB. Okay? How about the third term? The third term, A bar BC, I keep it as is. Okay? So I'm going this becomes this. And then the last one, A bar B. Again, I like to and a 1 with it. And therefore, it becomes A bar B ANDed with a 1. Okay? So we are done. And then my original equation, that was this one, is now what I'm showing down here, which is this. Which is this. Okay, now let's do this. Let's take the first two terms, these two here, apply distributive law, make it AC, okay, A and with C, and then factor out A and C, that's distributive law, that becomes 1 or B. This becomes this. And then take the third and the fourth, these two here, factor out A bar B, and this becomes this. One or B is the same as 1. 1 or C is the same as 1. AC ANDed with 1 is AC. A bar B ANDed with 1 is A bar B. Okay? Therefore, this changes to this. This changes to this. What do I have? I have reduced my original description, A and C, or B and C, or A bar B. I have reduced it to AC or with AB. What it means is this term wasn't even needed. The BC term wasn't even needed, so there is no point in having this gate here. Okay? What it means is 4 transistors for realization of this gate, that's if we do NAND gate, plus 2 transistors for the output, I don't even need those. This is my second example of Boolean algebra. I took this expression, played with this, and then turned the original description, turned the original expression, this, into this. Fewer transistors. Okay? That's my second example. And you are seeing the circuit here that realized using NAND gates. You're seeing the circuit is realized using 3 NAND gates. How do I do that? Well, we have seen that already, right? Notice that you can take the W output, double bar it, break the second bar, and then here is an AND, here is an AND, and these things are being NANDed together, and therefore this is this circuit over here. Okay? That was my second example. All right, let's do a third example for logic minimization. Let's look at this circuit. This is, if I were to build this, it would be 1, 2, 3, 4, 5 AND gates, and then an OR gate with 5 inputs. Okay, if we do De Morgan's or if we do bubbles, this will become 1, 2, 3, 4, 5, 6 NAND gates. Okay, let's see what we can do to do a little better. So for now, let's remember 6 NAND gates, and then a 2 input, 1, 2, 3, 4, 3 inputs, and then a 1, 2, 3, 4, 5 input. Okay, and perhaps counting the number of inputs, that would give us a good measure of how big the circuit is. So we have 12 and then 7 is 19 altogether, all inputs. All right, let's do the minimization here. Okay, let's erase this, clean this up. And this is how we go about doing the minimization. First of all, I have CD, and then I turn that into this. Nobody minds, right? CD ended with A or A bar. Remember, A or A bar is 1. Anything ended with 1 is that thing. So CD is CD. Nothing has changed. I'm not going to touch the second term. I'm not going to touch the third term for now. And the fourth term, ABC bar, I'm going to do something similar to what I did with the first thing, with the first term. I'm going to do with this, which is ABC bar ended with D or D bar. Okay, ended with D or D bar. There we go. And the last one, again, basically the same thing, ABD bar. I'm going to end it with C or C bar. Again, nobody minds. Okay. Let's go one step down, and then what I'm going to do is I have ACD, so nothing has happened from here to here. I have A bar CD. That means I'm using distributive law to expand this. So let me use the proper color. So I have this has become this, and the CD with A bar becomes this. Okay. The next two terms don't change. This is the same so far. Okay. This is the same so far. All right, so what I'm going to do next is I'm going to take A, B, C bar, ended with D, and then this becomes this, and then A, B, C bar, D bar, this becomes this. Okay. All right, the last two, it becomes A bar B, D bar C, which is this, and then A bar B, D bar C bar. A bar B, C bar, D bar. Okay, now let's go one step further down. What I'm going to do is the first term, the blue, this, and the green, which is the third term, A, C bar, D. Okay, I'm going to use a distributive law, and AD is factoring out, and therefore I end up with C or C bar. And then take the A bar C, which is again another blue, and then with the green, A bar C D, D bar. Yeah, the D bar on top of that is kind of hidden inside this. Okay. And there was another D bar here that I want to make sure it doesn't get lost. All right. So what I did was with the two blue ones, with the blue and one green, I came out with ADC or C bar. The next one is A bar, C, D, or D bar. So Let's go one step further. This becomes C or C bar is gone, so this becomes AD. A bar or C, D or D bar is gone, so this becomes this. Okay, so the first half of the expression really reduces to AD or A bar C. Now let's look at the second half of the expression. So I'm back in on this line here. So what I have is A, B bar, which is a red. Okay, see, A, B, C bar, D bar, A, B, C bar, D bar, A bar, B, C bar, D bar. Again, use distributive law using the factoring out B, C bar, D bar becomes B, C bar, D bar, A or A bar, and therefore these two, the red, right, and this become B, C bar, D bar. All right. So I'm going to write this here. The first half is gone. The second half, these two terms are gone. And I still have A, B, B, C bar, D to take care of. And also, I have A bar, B, C, D bar to take care of, which is this. Okay, this is what I have now. I'm going to take AD and factor out, take these two here. Okay, let me use the blue color. AD and AD from here. So that becomes 1 or B, C bar. 1 with anything is just 1, and therefore B, C bar drops, and therefore this whole thing reduces to this. Okay, notice that there is a bar C stuck somewhere in the middle, this one here. I take A bar C, and then I'll also have A bar C in this, and therefore factor out A bar C from these two, that becomes 1 or B D bar. 1 or B D bar, and therefore this reduces to A bar C. Okay. How about B, C bar, D bar? Nothing happens to that. It just peacefully goes from here to here and then to here. Okay. Let me show you the circuit now. The circuit is A, B, C, D. This is AD. A, D, A bar, C, B, C bar, D bar. Okay? And then these are ORed together. Okay, now I can do either De Morgan's or I can just do bubbles on the inputs and outputs of on the outputs of AND gates, on the inputs of the OR gates, turn it all to NAND. So let's do the ladder. A bubble here, nobody minds. You have a line with 2 bubbles on the 2 sides, nobody cares. A bubble here, same thing. A bubble here, same thing. I haven't changed the logic, but now this is an AND, this is an AND, this is an AND, and this is an AND. I reduced the circuit that had two, one 2-input NAND, four 3-input NANDs, five, and one 5-input NAND. I changed it to a 2-input NAND, a 2-input NAND. I'm not counting inverters at all. A 3-input NAND and another 3-input NAND. If I only count the number of inputs, this is 2 plus 2 plus 3 plus 3. That's 10. I started with 19 number of inputs. That means the circuit here is by far smaller than the circuit I had up there. If you want to count the number of transistors, even if you want to include the number of inverters, let's do as an exercise the number of transistors here. 4 here, if I'm doing CMOS. 4 here, 2 for the pull down, 2 for the pull up. 6 here, 3, 3. 6 here, and then 2 for the inverter. So I have 12, 20, 22 transistors altogether. And with the inverter. Let me do this, and then you do that as an exercise. 1, 2, 3, 4, 5. So I have 10 transistors on the outside. I have 1, 2, 3, 4. 4 times 6, 24 for the 3 input gates. Another 4 for the 2 input gate. And then A is complemented, C is complemented, B is not, D is complemented, 6 transistors for that. And therefore I have 44 transistors. If I were to realize the function using the original description, and if I minimize it and I implement this, I'll use half the number of transistors. Not only that, the delay of the circuit is less. The power consumption of the circuit is less. Okay? Very good. So I have all the good reasons to use Boolean algebra. What's the problem? Well, the problem is if I didn't know the solution, I wouldn't be able to reach this point. Okay? Just adding A or A bar, adding D or D bar, factoring this with the first one with the sixth one. Why would I do this? How do I know I have to do these factorings? How do I know I have to add D or D bar? Okay? Boolean algebra is good. The problem with Boolean algebra is that it doesn't give us insight into the circuit. It doesn't give us any guidelines as to how to go about minimization. And that's the topic of our next talk. Thank you.